Now we come to the third and last topic of this lecture, which is linear difference equations and linear recurrence relations. So a linear differential equation, difference equation, linear difference equation expresses a function yt unknown in terms of its past values yt minus 1, yt minus 2 and so on to yt minus n, and a known function, let's call it rt. So for example, we can have yt to be alpha 1 yt minus 1 plus alpha 2 yt minus 2 plus alpha n yt minus n plus rt. So here alpha i's can be constants, in which case this is a linear difference equation with constant coefficients, or polynomials in T also. So in which case, just as in the case of a differential equation, you can have coefficients which are constant or polynomials. Here also you can have constant coefficients or polynomial coefficients for the linear difference equations. And a linear recurrence relation, is a discrete version of a linear difference equation, and this can be written as an equals alpha 1 an minus 1 plus alpha 2 an minus 2 alpha n plus, so this is a constant term, plus some function r of n. So this is a known function. So in the first instance, here this is an equation in a continuous variable t, while this is the linear recurrence relation is in the discrete variable n. So this is the only difference between a a linear difference equation and a linear recurrence relation, and they are very closely related, because one can, if we are given a linear recurrence relation, we can always turn it into a linear difference equation. So we will see an example. So let's see how the Laplace transform can be used to solve such equations. So let's take a solved example. So we consider yt minus yt minus pi over omega equals sine omega t, where omega is a real number, is a constant real number, and we impose that yt equal to 0 for t less than 0, and this equation is valid for t greater than or equal to 0. So in order to find the Laplace transform for this equation, we can write this as yt u is the Heaviside step function here, u of t minus 0 minus y t minus pi by omega u t minus pi by omega equals sine omega t. We can write this because yt is equal to 0 for t less than 0. So both this is equal to yt and this is equal to yt minus pi over omega. So because the Heaviside unit step function is simply taking a unit step at, this one is taking a unit step at t equal to 0 and this one is taking a unit step at pi over omega, and before that it is 0. So this will conform to the fact that yt equal to 0. So you can write down the definition for these functions and find out that they will precisely give you yt for the first term and yt minus pi over omega for the second term. And now we will use the second translation theorem. Second translation theorem will give you, for the transformed equation, so for the first term we will get e to the power minus 0s times ys. So here ys, capital Ys, is the Laplace transform of yt. So this is simply ys, and the second one is e to the power minus pi by omega s ys, and the third, on the right hand side, we will get omega by s square plus omega square. So, and this is valid for s positive, so we can get the solution for capital Ys, which is omega by s square plus omega square by 1 minus e to the power minus pi by omega. And I'll just write down the solution for this Laplace transform. So the Laplace inverse of capital Ys is given by the function which is sine omega t if 2n pi over omega is less than t is less than 2n plus 1 pi over omega. So, and it is equal to 0 otherwise. So the first one is valid for n equal to 0, 1, 2, etc. So the graph of the function, graph of this function yt looks something like this. So it is sine omega t between, for example, if n equal to 0 here, you will get 0 on the left side and pi by omega on the right side. So 0 pi by omega, and it is 0 otherwise. So until it hits 2 pi by omega, this is 2 pi by omega, this is 0. So it behaves as sine omega t from 0 to pi by omega, and then 0 from pi by omega to 2 pi by omega, and then this function will repeat as t goes to infinity. So we'll have repeated such things. So this is a periodic function, and the Laplace transform for this function, let me call it ys again because it's the same function. This is equal to the integral from 0 to pi by omega sine omega t e to the power minus st dt divided by 1 minus e to the power minus 2 pi by omega s, because the period for this function is 2 pi by omega. So this is this whole interval where it is sine omega t from in the first half and 0 in the second half. So this is just applying the formula for the Laplace transform of a periodic function, and we will find that the numerator upstairs is given by omega by s square plus omega square 1 plus e to the power minus pi by omega times s divided by 1 minus e to the power minus 2 pi by omega times s. So here if you take e to the power minus pi by omega s as alpha, so this is 1 plus alpha and this is 1 minus alpha square. So one factor can cancel out and you will get 1 minus alpha in the denominator, which is simply 1 minus e to the power minus pi by omega. So this is exactly what we get here, and so our solution for the inverse Laplace transform is given by this function here. So in this way we can use the second translation theorem as a fundamental tool to solve difference equations like this. Now let us take another example. So let yt be a to the power the greatest integer part of t, greatest integer function of t, a positive number. So this is given by a to the power n if n is less than or equal to t is less than n plus 1, for n equal to 0, 1, 2 and so on. So I am going to consider it only for t positive. So yt can be, if can define it like this. So let us compute the Laplace transform for this function, transform for yt. So the Laplace transform of yt with respect to the variable t is equal to the integral from 0 to infinity a to the power greatest integer part of t e to the power minus st dt. And now we can break this interval 0 infinity into many integrals of length 1. So this will be sum n equal to 0 to infinity n to n plus 1 a to the power n e to the power minus st dt, and this is nothing but the sum n equal to 0 to infinity a to the power n e to the power minus n plus 1 minus ns minus e to the power minus n plus 1s over s. So this can be written as n equal to 0 to infinity a to the power n. If we take e to the power minus s from both factors, you get 1 minus e to the power minus s over s, and now this factor is independent of n, so it can be taken out of the summation. So this is equal to 1 minus e to the power minus s over s, n equal to 0 to infinity a e to the power minus s raised to the power n. So if s is large enough, a e to the power minus s will be strictly less than 1, and so which implies that one can use the summation formula for geometric series, which is 1 over, this is summation n equal to 0 to infinity alpha to the power n, and the formula is 1 over 1 minus alpha. So alpha is our a e to the power minus s. So the Laplace transform by ys is given by 1 minus e to the power minus s divided by s times 1 minus a e to the power minus s, and this is valid for s a over e to the power minus s less than 1. So for example, this means that e to the power s is greater than a, and if you take the log, supposing that a is positive, you can take the log on both sides, so s will be greater than log of a. So if a is greater than 0, if a is less than 0, we can still write it as a modulus, and we will have ln mod a if a is less than 0. So for this value, this Laplace transform is valid, and we get this as our Laplace transform for the function a raised to the power the greatest integer function of t. Now I am going to use this to solve linear recurrence relation. So let's take the recurrence relation. Let's take the following recurrence relation: a n plus 2 minus 5 a n plus 1 plus 6 a n equal to 0 for n equal to 0, 1, 2 and so on, and given the initial conditions a naught equals 0 and a1 equals 1. So we want to solve such an equation. So for this, let yt be given by a n, where n less than or equal to t less than n plus 1, and so we can rewrite the above equation as yt plus 2 minus 5 yt plus 1 plus 6 yt equals 0. Now if you want to take the Laplace transform of yt plus 1, this is equal to 0 to infinity y t plus 1 e to the power minus st dt. So if we change the variable from t to u with u equal to t plus 1, this will give us 1 to infinity yu e to the power minus s u minus 1 du, and this can be written as e to the power s integral 0 to infinity yu e to the power minus su du minus integral 0 to 1 yu e to the power minus su du. On the other hand, this gives us e to the power s, the Laplace transform of yt, minus, this is simply a0 because u is between 0 and 1, so this is simply a0 minus a0 integral e to the power minus s by minus s from 0 to 1. So this is e to the power s ys minus a naught 1 minus e to the power minus s over s. Similarly, we can find out the Laplace transform of y evaluated at t plus 2, and this will give us e to the power s Laplace transform of y t plus 1 minus a1 1 minus e to the power minus s above s, and this can be rewritten as e to the power 2s ys minus 1 minus e to the power minus s over s a naught e to the power 2s plus a1 times a naught e to the power s plus a1. So if we substitute these in this difference equation here, this is our difference equation 1. So substituting in 1, we get the following difference equation. We get the following difference equation: e to the power 2s minus 5 e to the power s plus 6 times ys equals e to the power s times 1 minus e to the power minus s over s, using the fact that a0 equal to 0 and a1 equal to 1 given as initial values for our recurrence relation. So we can solve this equation. So ys can be written as e to the power s 1 minus e to the power minus s over s times e to the power 2s minus 5 e to the power s plus 6, and the denominator can be factorized. It can be written as e to the power s minus 3 multiplied by e to the power s minus 2, and now I am going to take one factor of e to the power s on the numerator downstairs. So this can be written as 1 minus 3 e to the power minus s 1 minus 2 e to the power minus s, and again this is of the form 1 minus e to the power minus s times s 1 minus 3 e to the power minus s minus 1 minus e to the power minus s over s 1 minus 2 e to the power minus s, and both of these terms are of the form 1 minus e to the power minus s over s times 1 minus a e to the power minus s, and this was the inverse Laplace transform for this function was simply a raised to the power the function of the greatest integer function of t. So we get the solution as, so yt is L inverse of ys, and this is given by 3 to the power n minus, well, let me write it in terms of t first. So 3 to the power the greatest integer part of t minus 2 to the power the greatest integer part of t, and so since a n is yt for n less than or equal to t less than n plus 1, this implies that a n is 3 to the power n minus 2 to the power n. So one can check, so as an exercise, check that this solves the recurrence relation. So in this way we can also solve recurrence relation with the use of Laplace transform techniques. This brings us to the end of our Laplace transforms course. I hope you enjoyed the lectures and enjoyed learning about the theory of Laplace transforms. Even though this course was only for 4 weeks and we had only a short time to look at the theoretical and applicational aspects of Laplace transforms, still I hope you were able to understand and appreciate both these aspects and appreciate the power of the Laplace transform techniques. If you still have any questions, you can always ask on the discussion forum, and me and my team would be happy to help you. Finally, I would like to say thank you on behalf of the NPTEL team for taking this course and completing it. I wish you the best of luck for your exams, and I hope that you will be able to apply these techniques in whatever challenging problems you face in your own subjects.